All right. So last time, come on in to Co-17B. Yeah, no, it's totally fine. So last time we ended class doing an example where we were actually using the limit of the Riemann sum to actually calculate the area under a curve, which is something you might have to do at some point, but it's still good to see a couple examples. So to that end, there's a couple formulas you need to be aware of to do that thing if you want to do that thing. Or really, if your instructor wants you to do that thing, because do any of us really want to do it? Maybe me, maybe some of you, but probably not. So here are a few things we need to know about summation notation, which will definitely, that's not true, which will probably not come back in the future, but still good to be aware of. So this notation, the sum from I equals 1 to say 6 of 2I squared minus 3I, this is just an abbreviation. That's really what you should think of when you see this capital sigma notation here. It's an abbreviation for adding up a bunch of stuff. And the nice thing about this abbreviation is it has some rules that we can apply to make it easier to calculate things. So I'm just going to show you the shortcut, or I'm going to show you the long way to the shortcut here. If we write this out, what this says to me is first you plug in I equals 1. So I'm going to get 2 times 1 squared minus 3 times 1. And then you let I, which is called the index, and people use I, J, K, M, and N typically for the index, but any letter is a valid choice. This index here just increases to the next integer until you get to whatever that top one is there. So we're going to let I equal 2, 3, 4, 5, and finally 6. So writing this out, we're going to get 2 times 1 squared minus 3 times 1 plus, I'm going to use brackets just to break things off here. 2 times 2 squared minus 3 times 2 plus 2 times 3 squared minus 3 times 3. And the story goes on and on. 2 times 4 squared minus 3 times 4 plus 2 times 5 squared minus 3 times 5. Plus finally, I should make my example a little bit smaller, 2 times 6 squared minus 3 times 6. And yes, you actually could calculate this if you really wanted to, but that's not really the point usually. The point I actually want to show you here is that you can break this up. So I want to notice here that I have a 2 times 1 squared, a 2 times 2 squared, a 2 times 3 squared, a 2 times 4 squared, a 2 times 5 squared, and 2 times 6 squared. And I can certainly write that as 2 times 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared. Similarly, I have a minus 3 times 1, a minus 3 times 2, a minus 3 times 3, minus 3 times 4, minus 3 times 5, minus 3 times 6. I can certainly write that as minus 3 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. And then really what we're going to do here is we're not going to calculate that this is what, 21 and this is whatever it is. I think I have no idea what that is. We don't really care for the most part. But what I do care about is that we can recompress this. We can rewrite this as 2 sigma notations subtracted together. So this is 2 times the sum from I equals 1 to 6 of I squared minus 3 times the sum from I equals 1 to 6 of I. And I did do that in that last example on Monday when I was kind of rushing through the end of the problem. This is where that kind of idea comes from. You can totally break apart a summation of addition or subtraction into the addition or subtraction of those summations. Additionally, any constant multiples you can pull out in front of the summation. So skipping all this, you can do something like the sum from I equals 2 to 7 of 3I to the 4th minus 5I squared plus 2I. And we could totally break that up into 3 sums, all of them from 2 to 7. The first one being 3 times the sum of I to the 4th minus 5 times the sum from I equals 2 to 7 of I squared plus 2 times the sum from I equals 2 to 7 of I. The reason this is useful is because once you have these specific things, the sum of I to the fourth, or the sum of I squared, or the sum of I, there are formulas for those things. And I can't say whether or not it's just going to want you to memorize them or just know or give them to you or use them at all, to be perfectly frank. But I'll tell you a few of them because they come up. And they're kind of, and also really, because honestly, I think they're really neat, especially if there's a really cool relationship that we're going to see, I think. So here's a couple of these formulas, and then we'll use them to evaluate a couple of things. So the problem, I should say, the problem with this example, though, is the formula we're about to talk about actually is harder to apply here because all these examples started at 2. So like this here would be 3 times 2 to the fourth plus 3 to the fourth plus 4 to the fourth, all the way up to 7 to the fourth. And for the formula I'm about to show you to really work, you have to start at 1. You could fix it, but it's not really the point. So here are some summation formulas. I should say summation rules and formulas. So the rule we just talked about, it's actually kind of 2 rules in one. Here they are. So you can say the sum from I equals 1 to any integer later, positive integer, of some a sub I plus b sub I is the sum of the a sub i's plus the sum of the b sub i's. Right? If you do a1 plus b1 plus a2 plus b2 all the way to a sub n plus b sub n, that's the same as all of the a's added together, a1 plus a2 plus all the way to a sub n plus all the b's added together. Right? It seems reasonable. And the same is true if you subtract them. So really, we just like to kind of toss in an AI minus BI and the sum of AI minus the sum of BI there. So you can add or subtract summations by adding or subtracting the inside parts and vice versa. You can add or subtract the inside parts by breaking it apart. And then the other rule we kind of briefly talked about just now is the constant multiple rule. So really this constant multiple rule is kind of pervasive throughout every kind of calculus thing we do. The derivative of a constant times a function is just that constant times the derivative of the function. That happens all the time. We use it all the time. We've briefly mentioned how the antiderivative of a constant times a function is equal to the constant times the antiderivative of that same function. And it's true for summations as well. The summation from I equals 1 to n of some constant times your a sub I, and a sub I is kind of acting like a function here, right? A depends on whatever I you're putting in, and you're going to get a different value of a sub I for whatever I value you get. That's just going to be the constant times the sum from I equals 1 to n of a sub I. Again, we saw that above, right? We did here. Sorry, I can't see what I'm doing. I apologize for my lack of clarity where things are. But here, right, we had the sum of 2 times I squared and it ended up being 2 times the sum of I squared. It's totally fine to factor that 2 out from each term. Lose my papers here. And then we have some formulas. So here are some formulas. The first 2 should be not too hard to justify to yourself. If I take the sum from I equals 1 to n of 1, I'm just adding up 1 repeatedly. If you add up 1, how many times? N times. 1 plus 1 plus 1 plus 1 plus 1, n times is going to equal n. And you can generalize this further to just adding up a constant n times. So if you take the sum from I equals 1 to n of a constant, you're just adding up that constant n times, and you get n times that constant. And then the last time I also showed you, I know I was going very quickly at the end of class last time. that if you add up the first n integers, so 1 plus 2 plus 3 plus all the way to n minus 1 plus n, that's going to equal n times n plus 1 divided by 2. Yes, yes, thank you. You need to draw like, no, that's I should not draw this. There's a few ways to show this formula is true. I would refer you back to the end of last class if you're curious about how we did that, because I would like to show you two more formulas. One of them I will prove to you, and the other one I will just let us all believe it's true. So we typically want to know how to add the sum of the first n integers, or the sum of the squares of the first n integers, and the sum of the cubes of the first n integers. Those are the examples we typically limit ourselves to. Not that you couldn't go higher, you could, but we're going to kind of keep it there. So the question becomes, what's the sum from I equals 1 to n of I squared? Well, it's 1 squared plus 2 squared plus 3 squared plus all the way to n minus 1 squared plus n squared. Has anyone's instructor talked about this formula? Or at least said what it's equal to? Cool. It's probably something we should memorize. Do we need to actually prove it? Sure. Let me ask you all, would you like to see the proof? Because I'm really interested in doing it, but that's me, and this class is not for what I want to do because I think it's interesting. It's for what you want to see because it's useful. So it's okay. So who doesn't want to see the proof for this? It's okay. Oh, okay, so most of you do, I take it. That's what your not hand is telling me, that everyone would love to see the proof of this. Okay, great. So majority rules, plus that's what I want to do anyway. So I'll try to make it brief. You don't need to write this down probably. So here's how you prove this. Let's see, it's been a minute. Yeah, okay. So here's how you do this. We're going to do something kind of wacky. We're going to take the sum of I plus 1 squared minus I squared from I equals 1 to n. This is an example of what's called a telescoping sum, which means just, if you think about a telescope, how you like pull it out, you've got like a bunch of things. You can compress it all down to kind of the first thing and the last thing. Let me show you what that means. We start writing out terms. If I is 1, I get 2 squared minus 1 squared. If I is 2, I get 3 squared minus 2 squared. If I is 3, I get 4 squared minus 3 squared. And it keeps going on up until, let's say, n minus 1, where I get n minus 1 plus 1. So n squared minus n minus 1 squared. Finally, the nth term, n plus 1 squared minus n squared. And almost all of the terms cancel out. Negative 2 squared plus 2 squared cancels out. Negative 3 squared plus 3 squared cancels out. The negative 4 squared that I didn't write there cancels out with the 4 squared there. Similarly, at the end, the negative n squared cancels out with the positive n squared. The negative n minus 1 squared would cancel out with the positive n minus 1 squared before it. And so we're left with just two terms, n plus 1 squared and a minus 1 squared, which we could simplify. This is n squared plus 2n plus 1 minus 1. The ones cancel. You get n, squared plus 2n, which feels, no, that feels okay. Oh yeah, we're fine. Yeah. Okay, we'll leave it there for a second. We're going to calculate this a different way now. We're going to write this as the sum from I equals 1 to n of I squared plus 2i plus 1 minus I squared. Just multiplying out the terms inside the sigma notation. I squareds cancel. Now I'm going to use the rules I just talked about to break this sigma notation, the summation, up into two summations and factor out the 2 as well. So it's going to be 2 times the sum from I equals 1 to n of I plus the sum from I equals 1 to n of 1, right? The 2i is here. The 1 is here. Use the formulas we know. This is 2 times, we know that the sum of the first n integers is that formula we just talked about, n times n plus 1 over 2. And then the sum of 1 n times is just n. I'm sorry, my brain is thinking something. Oh, no, that's not. Okay. So these two things are equal to each other. Yeah, okay. Yeah. Sorry, I was like, sometimes you're like, how do I do this again? Oh, yeah, that's it. So, oh my gosh, oh my God, James. I think I'm proving the wrong formula here, such as life. Well, we'll do it anyway. So, yeah, really, James? Sorry, I apologize if this is the wrong formula. Sometimes you come to class, you're like, I'm going to do this cool thing. Yeah, I did. Well, sure. So here's another way of proving the formula that we already know. Sorry. So check this out, though. So this is the sum of 2i plus 1 from I equals 1 to n. And we can think of this as, well, if I'm trying to solve for this, then, yeah, that's, yep. Boo! Sorry. Oh, I hate it when I do that. I'm like, oh, it was so cool. And then, no, I did the wrong thing. So this, we could have proven this formula for this one by not knowing what it was, by saying it was equal to this other thing it's equal to, and then saying 2 times the thing we want plus n is equal to n squared plus n. Subtract n from both sides. 2 times the thing we're looking for is equal to n squared. So that's a 2n there. That's a 2n there. And then you divide both sides by 2 to get the formula that we already talked about. Bummer. Sorry, I was really like, I know how to do this, and then I did the wrong thing. So this is the sum from I equals 1 to n of I. So that's how you, another way of proving the formula we talked about at the end of class on Monday. Not as exciting as I was hoping for, and I don't think I should waste your time doing another thing that I just want to do for my own sake. So if you're really, really interested in knowing how you get that the sum from I equals 1 to n of I squared is equal to n times n plus 1 times 2n plus 1 divided by 6. I'll post it on Canvas and you can come see me in office hours if you're really, really intrigued. Yeah.
This is complicated, but is there any chance we could review period time equations?
Oh, okay. We're going, whoa, that's an interesting direct. Yeah, yes, certainly. It's just interesting that we're kind of going that way already. Sure. Yes, we can talk about that. Let me just say a couple more things here and then we definitely go that way. So the last one of these I'll mention is that the sum from I equals 1 to n of I cubed is equal to, this is the thing I think is really neat. It's n times n plus 1 over 2 squared. Or in other words, it's the sum of the first n integers quantity squared. So I think it's particularly interesting, just from a numerical perspective, not from a calculus perspective at all, that say 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, which is 1 plus 8 plus 27 plus 64, which is 100, is the same as 1 plus 2 plus 3 plus 4 quantity squared. I just think that's cool. There's really no other reason to know this other than using calculus sometimes. But like, it's always true. If you do 1 cube plus 2 cube plus all the way up to whatever number you want to stop at cube, it's the same as if you added up all those numbers and then squared the result. It's kind of wild. So anyway, let's do one example where we kind of talk about this again. So we actually calculate an area using these definitions, and then we'll probably call it quits as far as that goes, unless you are really, really hungry to see another example another time, because they are kind of tedious. So yeah, let's do this one. And let's not use that piece of paper. So we're going to calculate the area under the curve 3x squared plus 2x plus 5 on the interval from 0 to 2. That's what that means, by the way. right? When we write this integral notation here with limits of integration, which I know is kind of getting ahead of ourselves, but the problem with the integral stuff is we kind of move back and forth. Like, here's the area, and then here's how you do it, and then here's another way of doing it, and we kind of like say a thing that's not really a thing yet. But if I wanted to do this, I'm going to write this as a limit definition of a Riemann sum. In fact, I'm going to give you all a minute to find the thing. So I don't really care what my function looks like. Some parabola, okay, blah-de-da. I'm going from 0 to 2. It's not really ending at the vertex, but that doesn't really matter. And we're breaking this up into n sub-intervals. So there's my x sub 1, my x sub 2, my x sub 3, dot, 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 all the way to my last one being x sub n. And of course, my leftmost endpoint is x sub 0. So here my x sub 0 equals a equals 0. My x sub n, which is b, equals 2. Everybody should find delta x while I take a long sip of water. Here our delta x is going to be 2 minus 0 divided by n. It's kind of annoying, right? N is not just 5 or 100 or something. It's just n. You have to leave it that way. You can't just plug in a number for it. That's going to be 2 over n. And then to write this sum, it's going to be the limit as n goes to infinity of the sum from I equals 1 to n of the height of your rectangle times the width of your rectangle. Your f of x sub I times your delta x. So here's your first one, here's your second one, here's your third one. Each of those rectangles have a base of delta x, which is 2 over n, which I feel like this is too small. I can kind of do it there. There's a 2 over n. There's a 2 over n. There's a 2 over n. There's n of them, so it adds up to 2, which is how far it is from 0 to 2. Excuse me. And then each of these rectangles has a height of f of x sub 1, or f of x sub 2, or f of x sub 3, or so on and so on and so on. We're going to plug in the things. So my x sub I, well, depending on how you like to see this, I like to kind of talk it out. X sub 1 is just 0 plus 2 over n. X sub 2 is 0 plus 2 over n's. And we can start to see the pattern pretty quickly. X sub 3 is 3 times 2 over n. X sub I is I times 2 over n. Now, the messy part is going to be plugging this into the function. Right, I picked kind of a gross function, I'm not going to lie. Plugging this into the function, 3x squared plus 2x plus 5 means our f of x sub I is going to be 3 times x sub I squared plus 2 times x sub I plus 5, which is then going to be f of 2I over n is going to be 3 times 2I over n squared plus 2 times 2I over n plus 5. And we're going to take all of that, keep writing, James, and multiply it by the delta x, which is 2 over n. Questions so far before we get into the really nitty-gritty algebra part of it? That's going to be heinous, but fine. I want to remind you all I'm writing here is the height of the rectangle multiplied by the base of the ith rectangle. That's an n, by the way. We're adding them all up, and then we're letting the number of them get larger and larger and larger. So each of their widths get smaller and smaller and smaller, so the area gets closer and closer and closer to the actual area under the curve. I know it's like 3 ideas at once, but that's really what's. Okay. Now for the terrible algebra. It's algebra, not that bad. It wants to be your friend. So here we go. I really want to write all this every time. No, let's just simplify the insides. At the end, I'll tack on a limit and the summation. So let's simplify this. It's going to be 3 times 4i squared over n squared, plus 2 times 2i over n is 4i over n, plus 5, all multiplied by 2 over n. Distribute that, you're going to get 3 times 4 times 2 is 24 I squared over n cubed. I'm going to get 4i over n times 2 over n, which is 8i over n squared. I get 10 over n. I'm happy about this because each of my fractions has one higher power of n than the power of I. It's always what you want to happen if you have to do this terrible thing. Okay. So then we're going to say that the limit as n goes to infinity of the sum from I equals 1 to n of this expression, 24i squared over n cubed, plus 8i over n squared, plus 10 over n. We're going to break that up into how many summations? How many? I hear you whispering it. It is the number you're all saying quietly. It is 3. And I'm going to bring out the constant multiples as well. So I'm going to write this as 24 over n cubed. Yes, n is a constant as far as the summation is concerned, of I squared plus 8 over n squared times the sum of I plus 10 over n times the sum of 1. I know it's weird to think of n being a constant, but you're just saying there's n subintervals. N could be 1,000. N could be 5. But it's not changing as far as all of this is concerned until you take the limit, which is purely view of all of this. It's kind of annoying, but so now we're going to use those formulas we just talked about. This is the limit, as n goes to infinity, of 24 over n cubed times the sum of I squared, which was n times n plus 1 times 2n plus 1 all over 6. Here we're going to have an 8 over n squared times n times n plus 1 over 2. And here we're going to have a 10 over n times n. And now here's where you should do as little writing as humanly possible. Let me ask you all a question I want you to think about the answer to inside of your own brains. You should all be able to answer the question, what's the limit as x goes to infinity of 3x squared plus 5x plus 1 over 7x squared plus 2x minus 3? In your own head, think about what you think the answer should be. Oh, sorry, you can't see it. Sorry. Ugh, terrible. You guys really just say words. The KTs. Move the paper. So your answer should be a fraction. Hopefully everyone is thinking of the same fraction. The fraction is 3 over 7. The longer way of doing this work is to divide everything by x squared and then see that all the other terms are divided by x to the power and then going to 0 as x goes to infinity. The shortcut way of saying this is that when you have a rational function, the limit of the rational function is the quotient of the leading coefficients if those degrees are the same. So let me ask this then. For this expression here, is the highest power on top the same as the highest power on the bottom? Yeah, right. If we multiply it out, it sure would be. So this part here is going to be equal to, well, the leading coefficient on the bottom is certainly 6. The leading coefficient on the top is 24 times 2. I don't actually want to multiply out the top. I just want to see that this is going to be some 24 times 2 times n cubed plus other terms we don't care about. And this bottom part is 6 times n cubed. Same deal here. This top part here, you could probably multiply this out pretty easily. But it's 8n squared plus terms you don't care about. Yes, the other term is 8n. The bottom part here is 2n squared, and the limit of that's going to be 8 over 2. And finally, here, 10 over n times n is just 10. And this simplifies to 8 plus 4 plus 10, which is 22. And that's the area under this curve. Doing it the very, very long way. Okay. And unless you ask me to do it again, this will be the last time we do it the very, very long way. But we could totally do it again if you all want to do it. But with the, gosh, I can't see, can I not see the minute hand's like right behind the light reflection there? So I'm like, where is the minute hand? Okay. In the last little more than 15 minutes we have, Let's talk about, what was it? Pure time differential equations?
Right.
Okay. Pure time differential equations. The reason that your question threw me a little bit is because usually we don't start talking about, or like start calling them differential equations until a little bit later into the quarter. Totally fine though. So, what's a differential equation? What is a differential equation? It's an equation that has a function and I guess technically and or one or more of its derivatives. So it doesn't actually have to have the function proper, but it has to have at least the function or one of its derivatives. Usually both. Usually you have the function and its derivative or its second derivative, etc. So here's an example of a very important differential equation. Oh, you said pure time though. Okay. So here's a non-example of a differential equation. dy dt is equal to y. This is not pure time. And the reason it's not pure time is because the derivative depends on things other than just time. End of story. I will point out, I'll point out. Because this is going to come back later. We're definitely going to talk about differential equations later and how we solve them. I will note here that the general solution to this differential equation is y equal to c e to the t. And I will say more explicitly that when we're solving differential equations, the solution is typically a function, right? This is the answer. Where the question is, what function satisfies that the derivative of the function is equal to that function? Oh, that seems reasonable, right? E to the t times the constant is the function that if you take its own derivative, it's still the same thing. So this differential equation, this not pure time differential equation, this would be an autonomous differential equation. Has that solution. So autonomous differential equations are differential equations where the derivative of your function depends solely on the function itself. Question.
Is like implicit differentiation form?
No, not. So it's really so again, I'll say these words again. So when we talk about a differential equation is an equation that involves a typically unknown function and or one or more of its derivatives. And then I will say that usually your goal when present, not always, I mean, it depends on how the question's phrased, but usually when you're dealt a differential equation, you're usually being asked to solve it by finding the function. So we try to solve them by finding the function, typically y. So if you're writing dy dt, y, the function is the dependent variable, t, the independent variable is the other variable is the independent variable. The one in the, I don't want to say numerator, the one on the top of the derivative is the dependent variable, which is the function. The one in the bottom of the derivative is the independent variable. So if I wrote, say, dy dx equal to, sure, it's to me less exciting, but fine, equal to cosine of x, even though I didn't use the letter you might prefer, we would call this a pure time differential equation. because the derivative of y depends only on the independent variable x. So you could say this, or if you prefer, you could say dy dt equals e to the t plus 5t. Both of these are examples of pure time. What can I spell? Not really. Differential equations. Because the derivative only depends on the quote unquote time variable, or more generally, the independent variable of the derivative. The nice thing about these differential equations is they're the ones that are kind of the easiest to solve. We can solve these by simply just anti-differentiating. I will point out that's not always going to be an option later on when we start when we start trying to solve differential equations that are not just pure time. The pure time ones are the nicest. So we could solve both of these readily just by anti-differentiating. So if I was going to solve dy dx equal to cosine of x, all I'm really saying is the derivative of my function equals cosine. And I'm pretty sure I know a function whose derivative is cosine. It's y equal to sine of x. Let's see. If you want to be a little bit more of a stickler for notation here, you could say, well, James, I'm going to separate my variables because that is the thing we do when we solve differential equations. And essentially write this as dy equal to cosine of x times dx. Just multiplying both sides by the dx. Even though, again, I'll say this more than enough times probably. Dy dx is not a fraction. I know it looks like a fraction. I know we treat it like a fraction. Most of the time it works like a fraction like you want it to, but it's technically not a fraction. But we're going to abuse it like it's a fraction all the time. So dy dx, as far as we're concerned, you can treat it like it's a fraction because it works like that in almost any instance you need it to. And then what we're going to do here is we're going to anti-differentiate both sides. And the antiderivative of 1 dy is going to be y. Because the derivative of y is 1 if you're differentiating with respect to the variable y. And the antiderivative of cosine of x is sine of x. And then we add on a plus c. That's kind of the long way to get there. But again, for pure time differential equations, you really don't need all of this machinery here. You can just say, hey, we're anti-differentiating. So for example, if I was trying to solve the differential equation, dy dt equal to e to the t plus 5t, I know I'm just trying to find the antiderivative of e to the t plus 5t. So my solution here would be y equal to the antiderivative of e to the t plus the antiderivative of 5t plus c. What if they said, or actually I should say, these are both general solutions to this differential equation. But if they then told me additionally, hey, also, I'm going to tell you that for this particular example here, we know that y of 0 is equal to 17. Find the constant. It's not very exciting here, but okay. So if I plug in 0 for t and 17 for y, I get 17 equal to e to the 0 plus 5 times 0 squared over 2 plus c. So what's c equal to? You don't have enough fingers, sorry. Someone has to say a word. Almost! Yeah, because e to the 0 is 1. So be careful. A lot of times it's easy to get into the habit of like, oh, I plugged in 0, everything is 0. But sometimes like with e to the 0 or cosine of 0 or other things where you plug in 0, you don't get 0. So just be extra careful when you're plugging things in. So we have 17 equal to 1 plus c. So yes, 16 is equal to c. And so then if the question was, tell me the particular solution, you can't just say it's 16 equal to c. You have to say, oh, the particular solution here is the function with that actual c value plugged in. My particular solution here is y equal to e to the t plus 5 halves t squared plus 16. Or if you're like me, you might prefer to be more explicit about the functional relationship here and write it as y of t equal to e to the t plus 5 halves t squared plus 16. Either way is correct. I just think it's a good idea to write y of the variable so that you're really emphasizing the fact that you know that it's a functional relationship. So long story short, pure time differential equations are really just anti-differentiating. But they are a little bit more challenging in that sometimes you might be asked to solve them and then use an initial condition to solve for your constant c. It would be even more challenging. Do we really want to do that? No, not really. But someone might ask you to do something like this. That's not lovely though. I don't like it, but I'm gonna do it anyway. So find f of t given that f double prime of t is equal to, I'm trying to make this not too terrible here. Sure, let's make it. Fine, James, fine. Let's go that way. 6x squared. Is that what I really want? No, I want 12x squared. Sorry. 12x squared. Sure, that'll probably work out fine. Minus 6x plus cosine of x. And of course, I made the classic mistake of saying f of t and then writing x's instead. Sorry about that. Let's change those x's into t's. That's a 12t squared. That's a 6t. It's awful is what it is. Plus cosine t. And we are told that f of 0 is equal to 3. And f of, that's going to be awful. Sure. Now let's do f prime of 0 just to make life less terrible is equal to 7. Okay. So we want to find the original function. We have the second derivative. To get to the original function, we're going to have to anti-differentiate twice. So if we anti-differentiate, the antiderivative of the second derivative is the first derivative. If f prime of t equal to 12t cubed over 3 minus 6t squared over 2 plus sine of t plus a constant. And then we could simplify this, and you should simplify it, especially if you're going to have to take the next antiderivative. It's definitely worthwhile to spend some time simplifying here. That's going to be 4t cubed minus 3t squared plus sine of t plus c. Since I was lucky and they gave me f prime of 0, which isn't always the case, they could have given me f of 0 and f of something else, and it would have been a little harder to solve this. But they didn't do that here. Since they told me f prime of 0 is 7, I can say, great, f prime of 0 is 4 times 0 cubed minus 3 times 0 squared plus sine of 0 plus c, and that's equal to 7. That's 0, that's 0. What about that? Ooh, sine of 0. It is 0. Unit circle time. The c equals 7. Great. And then we anti-differentiate again. And we get f of t equal to the antiderivative of 4t cubed, which is 4t to the 4th over 4. Or you could just have said t to the 4th minus 3t cubed over 3. Same common applies there. Plus the antiderivative of sine of t is negative cosine of t. And I would have just written minus cosine of t if I hadn't already written a plus sign. Plus another constant, which I would call a different name. Even, wait a second here. Sorry, that's 7 right there, so apologize. The antiderivative of 7 is 7t, and then plus a new constant. The reason I would use different letters here is that occasionally you won't know what c is. And if you didn't already know what c is, then when you anti-differentiated this, you would say that the antiderivative of c was c times t plus a new constant t. And you want to use different letters there because they're probably going to be different values. And then you would plug in 0 for t again, f of 0. Let's be smooth about this. That's going to be 0 minus 0 minus cosine of 0 is minus 1 plus 0 plus d, and that's supposed to equal 3. Adding 1 to both sides, you get d equal to 4. And then the final answer is that the function f of t is t to the 4th minus t cubed minus cosine of t plus 7t plus 4.